All right, so welcome to lecture 22. This is chapter 6, section 1. And we are going to be talking about electromagnetic radiation. I'm going to go ahead and apologize right away for my writing. The battery on my stylus died, and the battery store is closed at the moment, but I want to get as much of this done right now as possible. I'll buy a new one tomorrow. Fortunately, this is not a math-heavy lecture, so we can hopefully power through. But electromagnetic radiation. So, a couple of observations led people to realize that light is like a wave. Namely, light can go around corners. Okay? If you have, a wave traveling and it comes to a corner, what's going to happen is it's going to bend so that it can go around the corner. And light obviously does that. Light goes around corners easily enough, even when there's nothing to reflect the light, so it's not bouncing off a wall over here and heading over to that way. You can still see thanks to a light around the corner. Not necessarily well, but you can see. The other thing is that you'll get something like this. Okay? If you have a wave traveling toward a wall with a slit in it, then on the other side of the wall, it'll start, spreading out away from that slit. Ocean waves do this, but so does light waves. And more importantly, you get an interference pattern. Now, an interference pattern is a result of something like this. Okay, the S1 and the S2 down here in the bottom, there's two green dots. Those are source 1 and source 2. Those are the places where the waves are originating from after they pass through a slit. So what's happening is that instead of having one hole in the wall that the light or the ocean water wave is coming through, you have two. And so you get these two expanding rings of waves. And you get an interference pattern where, either crests line up with crests and troughs line up with troughs, or crests will line up with troughs. And what happens is when, they add crest to crest, they get bigger. And when it's trough to trough, they get smaller. Okay, so what you're getting is, these lines where they are, either, perfectly adding together, such as the blue lines are where they're canceling out. The red lines are where they're adding together, okay? It's probably fairly hard for you to see there on the YouTube video. But the blue lines, every dot is a place where a peak is adding to a trough. The red lines, every dot is where two peaks come together or two troughs come together. And thus, when they hit the wall, what you see with light is something like this. Okay, places where the light adds together, you get these bright bars. Places where the light cancels out, you get dark bars. Okay? And that's called an interference pattern because the two sets of waves are interfering with one another. Either constructive interference makes the bright lines, or destructive interference makes those dark lines. Okay? So water waves do this and light waves do this. If this was water, instead of bright bars, you would get like really, really big peaks and troughs, places where the water was lapping really, really high against that far wall. Okay? And places where it's dark, the water wouldn't be moving at all. Okay? You would just be perfectly still. Okay, so that's how they knew that light was a wave. So light has a number of properties. Waves, I should say, have a number of properties. First off, you have wavelength, okay, represented by the Greek letter lambda. Lambda represents wave length. Wow, so my cursive marks, okay. Anyway, wavelength is the distance from peak to peak or from trough to trough. Okay, so that is your wavelength lambda. You also get what's known as frequency. That's not the letter V. It's actually the Greek letter nu. Looks a lot like a V, so I'll try to make sure to distinguish it whenever possible from the letter V. But this is frequency. Okay. And frequency tells you when you have, waves passing by, how many times per second does a peak or a trough pass by a certain point. So how often? Okay, so whereas, wavelength is measured in meters, frequency is measured in per second. Okay, that's cycles per second or something per second, items per second, just per second, or seconds to the negative first. Or, just to keep people from feeling awkward, they use hertz. Hz, the hertz, is just the same thing as 1 over seconds. Okay. So together, wavelength and frequency give you speed. Okay, so the speed of your waves is equal to lambda nu, wavelength times frequency, and that gives it units of meters per second. Okay? Meters times 1 over seconds gives you meters per second. Now, for ocean waves and for sound waves, speed is determined by the medium. And that is to say, what they're traveling in. So ocean waves, you have the water being pushed up and down by the energy. The water itself is the medium. The energy is traveling through the water. The water actually stays put. Okay, it'll go up, it'll go down, and then it'll end up right back where it was. Similarly, for sound, what you get is places where the air is more dense and places where the air is less dense, more rarefied. Okay, so it is a compressive wave. Okay, but it's very similar in that way because, you can treat the compression as a peak, the rarefaction as a trough, and it's very, very similar. It will also have a wavelength, it'll have a frequency, and it'll have a speed. Okay, so the speed of sound in air is, I believe, about 300 feet per second. And the speed of these waves depends on the medium. The speed of sound in, say, underwater is much faster than it is in the air. And it's even faster in something solid like steel. Okay? And the last property, so speed and frequency are two of the properties, or sorry, not speed and frequency, but wavelength and frequency, lambda and nu, are two of the properties of the wave. Speed is not an independent property because it's based on the other two. So, but the third is amplitude. Amplitude. This is the letter U. Okay. And if we represent that at all, we represent with A for amplitude or possibly I for intensity. Okay, and that just tells you how high your wave is. Okay, so the straight line here is the 0 mark. That's the normal place. And then amplitude is the height of the wave. Now, light has all of these things. Of all of them, amplitude or intensity is probably the easiest to measure. It's just how bright is your light. For an ocean wave, it's how far up and then down, or down and then up, does the water go. For a sound wave, amplitude would be volume. How loud is the sound? Okay. So those are your three properties of a wave. Lambda, nu, and A. Wavelength, frequency, and amplitude. And the units of amplitude depend on what kind of wave you're talking about. Now, for your ocean wave, or your sound wave, or what have you, energy is related to amplitude. Energy tells you how much energy is stored in your wave. Okay? The louder your sound is, the more energy there is in that sound. The taller the ocean wave, the more energy there is. I mean, think about it. The water wants to rest, flat and level. In order to pick it up or push it down, you have to put a lot of effort in. So that's how much energy you're storing inside your wave there. Okay. So that was the classical conception of light. Was similar to an ocean wave or a sound wave. They didn't necessarily know which one it was, but obviously it behaved like waves. It went around corners. It created those interference patterns. It has an amplitude or an intensity, so it behaves like a wave, and that's how they thought of it. They were kind of wrong. One of the things that came out of this was the belief in the luminiferous, that's E-R, luminiferous ether, the luminiferous ether. Because as far as they could tell, all waves require some medium to be transported in. Therefore, if light is a wave, there must be something in outer space for it to travel through. So that's where they came up with the luminiferous ether. We'll see in a bit that the luminiferous ether is garbage. It does not exist. But that's what they thought. And this was the classical model of light. Light is kind of like an ocean wave. And I want to stress, they weren't stupid. This was based on real observation. Light is behaving like a wave. But then there were other observations that didn't cooperate, that didn't really work out. So first off, we have what's known as black body radiation. Okay. Namely, if you heat something up, it glows. Okay, you've seen this anytime you turn on the stove and it turns red, or you turn on an old-fashioned incandescent light bulb and it makes a lot of light. You get something hot, it glows. The hotter it is, the brighter it glows, and it also changes color. Okay, so that a cooler thing glows red, and as it gets hotter, it gets yellower. It goes through bright cherry red, then it starts to get sort of golden, then bright yellow, then it gradually becomes a bright white color. As it gets very, very hot. The reason they call this black body radiation is because that's named after the ideal model they came up with, for an object that absorbs light perfectly. And if it absorbs light perfectly, it will also irradiate light perfectly. So that was their ideal model. And if it absorbs lights perfectly, then it's going to be perfectly black, the blackest thing you have ever seen. So that's black body radiation. Now, being physicists, they tried to come up with a way to mathematically model the radiation that came off of these things. They had spectrometers. They could measure intensity, and they could measure the color of the light coming off of an object. And, what they saw was, things that looked kind of like this. These are getting hotter and hotter, so this is cold. And this is medium, and this is hot down here on the right. So they were trying to come up with the formula, the mathematical formula that would model that. Now, it didn't work. Long story short.